Well, hello there. So let's look at these first order equations applied to inductor circuits. So we're going to look at an RL circuit that has resistors and an inductor, a single inductor, and it will parallel very closely the RC circuit analysis that we just did. So remember the RC circuit that we just did. Our process was to analyze the circuit with DC steady state. We needed the initial conditions for sure, and we could also find the final condition, the infinity condition, if we wanted to. Then we found a Thevenin circuit for everything except the one capacitor for the t greater than t0 or t greater than 0 condition. That Thevenin voltage is the final voltage that we might have already found up here. And then we have a cookbook for the response. So voltage across the capacitor as a function of time is a function of the final voltage, the initial voltage, and the time constant. So we want to take that same approach for inductor circuits, RL circuits. So a circuit with a single inductor we can handle in the same way. So much like a couple of videos, we'll start with a natural response, which is when we charge up the inductor, create that magnetic field, and then let it discharge naturally what we get. So first we want to find the initial condition, the initial current through the inductor. So remember, everything with capacitors is the opposite of inductors. So we find the voltage across the capacitor, so we're going to find the current through the inductor. Just they're kind of complements of each other. So we need the initial current through the inductor. And with this circuit, it's easy to see that in DC steady state, this becomes a short circuit. And so all the current is going to go through here and none through there. So we have IS initially. For greater than 0, we have to do the analysis. So we move the switch at t equals 0 down here, which means the inductor is left just with the single resistor. If we analyze that circuit, Kirchhoff's voltage law says the voltage across the resistor using Ohm's law plus the voltage across the inductor using its differential equation has to sum to 0. And we can put this into our standard form with a 1 in front of the derivative term, and we get this homogeneous first order differential equation like we've seen before. And using the same process, we can find the function of time. So again, the process starts with initial conditions, then we analyze the circuit and hopefully find a cookbook equation. Here's the more useful one, the general response of the RL circuit. The circuit is kind of complicated. You can see we have a single inductor here. There's a resistor in parallel with it. Got a switch in the middle, two current sources, and another switch over here. So at t equals 0, switch 1 goes from 1 to 2, so it switches this current source out, and switch 2 goes from 1 to 2, so it switches this current source in. It doesn't matter, we just analyze them for before t equals 0 and after t equals 0 and draw them to get rid of the switches. So initially we want to find the current through the inductor. So for the steady state value, for t less than 0, the inductor becomes a short circuit. That's its DC steady state condition. And you can see we have a resistor in parallel, but it's all going to go through here because it's easier. None of this is doing anything before t equals 0, so IS1 goes through L. So our initial current, IS1. Then we look at the circuit for t greater than 0. And we have the switch over here, and the switch over here. So this is not doing anything, and this is not doing anything. So we have the current source with a resistor in parallel and an inductor in parallel. So this is a Norton equivalent circuit, and current source and a resistor in parallel. So if we can analyze this, we can do it for any Norton equivalent circuit. And we do, again, Kirchhoff's current law. The node up here, IS2 is coming in, so it's a minus sign, plus IR going out, plus IL going out has to equal 0. Then we have the same voltage across the resistor and the inductor, so we can use their equations and find this format. So di dt plus A times I equals B, and A is the same A that we had in the previous slide, and B is given by this equation here. So the solution to this first order differential equation we went through before in terms of V, but it's the same if it's an I or a V or an X, and so we can use that same result and find the current as a function of time through the inductor. It's a function of the initial current, the final current, and the time constant tau. Here tau is going to be L, the inductance, divided by our Norton resistance. So we've got our cookbook solution, so let's summarize it. So here again, for t greater than 0, we have a Norton equivalent. This is Norton resistance, Norton current, and the inductor looks like a load. So the final steady state current in the inductor is the same IS2. So if you find the Norton, you've got the final infinity current. And we can use this equation with the infinity current. The initial condition really depends on the initial circuit, which is different from the final circuit. And the time constant tau, that's L over R, where R is our Norton equivalent resistance. Okay, so the final summary here of the RC and the RL circuits. For the RC circuits, we find the initial and final voltage on the capacitor using DC steady state values, where the capacitor becomes an open circuit. Make sure the switches are set up right. That gives us V0 and V infinity. Then we make a Thevenin equivalent of the circuit using the capacitor as the load and find the Thevenin resistance that gives us our time constant when multiplied by the capacitor. And then we plug in and we've got our answer. For an RL circuit, we find the initial and final current through the inductor using DC steady state, where the inductor is a short circuit. Make sure the switches are set up right. Then we make a Norton equivalent, or you could also do a Thevenin because it's really only the resistance that we need of the circuit for t greater than 0, and use this cookbook equation where tau is L, the inductance, divided by the Norton or Thevenin resistance. So that's the approach we're going to take. You'll get to do it for homework, and I'm sure this will come up on an exam, so make sure you get these equations somewhere handy. Let me know if you have any questions, and I'll see you in the next video.